Unlike most of my videos, this one isn't tied to a particular topic that we learn in class. Instead, it's related to a particular concept that appears at 3 different times during this course. 3 of Maxwell's equations use the conceptual idea that the field, either an electric field or a magnetic field, on the boundary of some region, which could be a volume or an area, is due to the amount of something, charge or current or another field, within that region, that is, within the volume or the area of that region. For example, Gauss's law, the first one that we encounter and the one that we're working on when you see this for the first time, says that the electric field through a closed surface is due to the charge in the volume enclosed by, that is, within that closed surface. Ampere's law, that we encounter twice in this course, says that the magnetic field around a closed loop is due to the current flowing within the area enclosed by that loop, or much later, the E field that is changing within that loop. Faraday's law says that the electric field around a loop, that is, again, around a closed loop, is due to the changing magnetic field inside that loop. Now, although the physics and the mathematics is different for each of these, they share a common concept and a common conceptual problem: how to figure out what is inside. This is a problem that's solved by thinking, not equation grabbing. That makes it a particular challenge in any introductory course. Now, there is a mathematical approach. That approach is based on setting up and doing the relevant 2- or 3-dimensional integral. Integrals that one first encounters in Calc 3 and in Calc 2. In Calc 2, there are things like volumes of revolution. In Calc 3, there are actual true volume integrals. However, setting up those integrals also requires thinking. You have to figure out exactly what the various boundaries are, and in particular need to know the appropriate 3D area or volume element that applies to that particular physical situation. So it doesn't really solve the problem. In fact, the essential element there is the same. Now, I believe it is more effective to approach this as a problem in set theory, because what you actually need to do is add up, that is integrate, the amount of something in a region that's the intersection of 2 sets. I come up with this idea from my background in quantum mechanics, where one regularly deals with what's called an overlap integral, which is an integral that looks at the overlap of several different functions that represent physical quantities in a problem. And that's effectively what we got here, except that we really only have a single integral, and we're looking at the overlap of the area or volume that's sampled by that integral and some physical quantity within that volume. That said, if you learn this approach, you'll be able to assess whether you've correctly set up a 3D integral, whether it's in Calc 3 or in a more complicated physics problem that you might encounter in either physics or engineering or chemistry for that matter. The basic idea is a very basic one, the intersection of 2 sets. I'm told that many of you learned this in English class in high school in this state of Florida, and given that, it's not surprising that you don't associate something you learned in English with something that you're going to apply in either mathematics or physics. But that is the case. It's a basic mathematical idea, and you need to understand it to do physics. So here's 2 sets. Set 1, a blue rectangle with a dark blue border, and set 2, a red circle with a dashed boundary and a sort of dotted stippled area inside. As drawn right here, they have no overlap, so their intersection set is the empty set. If I move them so they overlap, now there is an intersection region. It's the overlap region between these 2 sets, and it's been shaded with a diagonal red line on top of the same blue background you see in set 1. That intersection region contains points in both sets. That is, it's in the rectangle and it's in the circle. Points that are in the rectangle but not the circle, or points that are in the circle and not the rectangle, must be excluded. That is the fundamental idea of an intersection of 2 sets. Now, a typical problem for us involves 2 circular regions. A region that's inside, say, R, the radius, the point where we want to know the field, and, that's the important thing that means intersection, and the region where the source of the field, the charge or the current, or another field for that matter, is not 0. So we're looking at an area inside R and an area where something else is not 0. So here's a possible field source. Early in the course, you'd recognize this as being a hollow sphere, for example, or a hollow cylinder. Later on, it might be a hollow conductor. The light blue area is an area where there's a non-zero field source, let's say an electric charge or an electrical current. Now, the red area I'm going to use here, the circular area, is the area that is inside R. So that dashed red line represents points where you might be calculating the field. When we overlap these two, find their intersection, the shaded blue-red region, the region with the diagonal red hash lines through it, is the enclosed source. It's the area that is both inside the red dashed line and has a non-zero blue area. And with R outside that source region, all of the source is enclosed. Sometimes that's enough to answer the question. What formula do we use? The one appropriate to the geometric object that describes the shaded region. In fact, it might not even be a formula. It might just be, oh, all of the charge is there, or all of the current is there. Now, for the same field source, but a different value for R, when we overlap them, we get this situation where now there's a part of the blue source that is outside of R, outside of the red area, and therefore doesn't overlap with it. There's a region inside the center where you're inside R, but there is no blue source. Only the diagonal shaded area is in both of the sets. And that's the area that we care about. That's the area that's got the source, the part of the source that's inside R. Say that back up again. Only part of the source is inside R. That's the part that gets shaded. That's then the part that we need to calculate. What formula do we use? The one appropriate to that particular object, that particular shape. It might be a volume or an area. And again, for the same field source and an even smaller value for R, when we overlap these two, we see that there isn't an overlap. There are no points that are light blue that are inside the shaded red area, and therefore the empty set is the intersection of these two sets. With R entirely inside that particular source, none of the source is enclosed. What formula do we use? Well, not really a formula, it's zero. Again, you think, and you say, well, how much is there? Nothing is there. The answer is zero. However, with a different field source and the same small value for R, now there is an overlap region and there is an enclosed source, and therefore there is a source that we need to calculate the amount of. And for this, you use the formula for this particular shape, which might be the area of a circle or the volume of a sphere. Depends on the geometry of the problem and the specifics of the physics problem we're doing. So to summarize, this is mostly one big interpret step. You identify the region inside, identify where the source is not zero, identify the overlap of these two regions, and then, and only then, develop the formula for the source of the field that you're trying to calculate.